So Gary, you were kind enough to show us the rather rudimentary functions and how to do that in MLAB, and now we're looking at chemical kinetics, and in particular we're going to look at a do file which represent a modeling of a second order binding.
Okay.
Take us away.
Here we go. So we're going to run MLAB again, click. And now we're going to go to top level MLAB again, continue. And we're going to look at a actual modeling of data where we estimate certain parameters in chemistry or pharmacology. And to begin with, what we're going to do is say do step equal 1. The reason we do this is we want to execute the commands in our do file, i.e. in our script or our program, one line at a time, so you can see them on the screen and we can discuss them as we're going through them. So having set do step equal to 1, we're now going to say do the commands that are found in the file sob example.do. And nothing's happening, but if I hit the return key, I see finally the first printable line of the file, and it's just a comment line. The /* */ is a comment, and it says we have a file called sob example.do, and it is a simple binding study. And there's some more comments, /*. Notice the comment spans multiple lines here. There's no */ yet. And we'll just go right on through it until we get to the very bottom. There we are. And if we look at this, I'll use my mouse as a pointer. All we're saying is that we're given data of the amounts bound, that's B, measured at different times when we have the chemical reaction F, some ligand, binding to G, some other material, some site molecule, let's say, where we have F0 moles per liter, i.e. molar units, of the F material, and we have G0 molar units of the G material. That's how much we mix together, F0 and G0. And we also have B0 molar units of the B material. Now, in fact, we're going to take B0 equal to 0. We're going to mix F with G and not have any B when we start. But we could have some B when we start. It would be perfectly modelable. Now, this reaction, F plus G goes to B, has an association constant, K1, which says how much the F and the G like to stick together to form a B. And there's another constant, K2, called the dissociation constant, which says how much a B molecule likes to come apart into an F and a G. We won't say anything here today about the units of these numbers, but suffice it to say they are very important numbers. If you know K1 and K2, you know essentially everything you need to know about the time course behavior of this chemical reaction, F plus G goes to B. And by the way, just for those of you who remember your chemistry, the equilibrium constant, Ke, is the ratio of K1 to K2. Now, the differential equation model that describes the reaction F plus G goes to B and back again is this. It is the rate of change of B with respect to time. We write that B prime t. That's the derivative of B with respect to t. B is a function that says how much B there is at time t. But we don't know what the B function is here. We just know its derivative. And its derivative is K1, that association constant, times the amount of F at time t, times the amount of G at time t. And that's basically the creation term, the positive term that adds a positive number to the derivative. Minus, so this is the negative term, this is the destruction, K2 times the amount of B. So in other words, the bigger the amount of B is, the amount of that B that will change instantaneously back to F and G is proportional with the proportionality constant K2. Now, in fact, what is F of t? The amount of F at time t is equal to the amount of F you start with that's free, that's F0, plus the amount of F that's bound up in the B, you have to count those F molecules, that's B0 at the beginning, minus the amount that's bound right now. Well, whatever's not bound right now, that's B at t, must be free. So therefore, the free F at time t is equal to the total amount of F you put in minus the amount that's bound right now. Notice at time 0, this is F0 plus B0 minus B of 0, which is just B0, is just F0. Okay, similarly, the amount of free G, the G that isn't bound to anything, is the amount you put in plus the amount that's bound up in the initial amount of bound material minus the bound material at time t. These are functions of t. Okay, everything depends here on knowing this function b. B of t, B of t. B of t is appearing up here, implicitly appearing in the f and the g, but all we know is its derivative. Now, in fact, this differential equation, which is what this is, can be solved for the b function. It's not a very simple solution, and with just a little more complication in this, it can't be solved at all. So it's really much nicer to use differential equations to describe chemical kinetics than it is to try to use the solutions, even in those cases where the solutions can be found. Okay, continuing, let us note that if we substitute this function f of t in terms of b, g of t in terms of b of t, we get this equivalent differential equation. The derivative of b with respect to t is a function of time, is equal to k1 times the free f. Remember, that's just f0 minus the amount that's bound at time t. Notice here we just write b. We don't write b of t. We could, but we don't have to. It understands that it's b of t. Which is traditional 19th century mathematical notation, by the way. And minus b of 0 is just plus b of 0. So f minus b0 is the same thing as f plus b0 minus b. Similarly, the free g is g0 minus b0. And the term minus k2 times b is just minus k2 times b again. That's the destruction term. This is the creation term. And finally, we have to say what the initial value of b is. How much bound do you have at time 0 when you start the reaction? And we have 0. We just mix f and g together.